Thank you. So this presentation is based on our recent work done with Natalia Żywódzka, Volodya Marchenko, and Javier Pascual Granado from Spain. And the last part of the talk will present some preliminary results on gamma ray bursts. So I will start by describing the Lomskargul periodogram, followed by an overview of wavelets, and next define the AT plane. As an example of a QPO search, I will discuss the case of a Seyfert 2 barred galaxy observed in X-rays. I will then present some of our results concerning the Fermi-Lad gamma ray light curves of some blazars, and finish with the already mentioned preliminary results regarding prompt light curves of swift gamma ray burst. Okay, so as a first reminder, if we are given a time series of n observations at times t, which do not have to have a constant time step, in fact the gaps can be even completely arbitrary, one constructs the periodogram algorithmically just by plugging the data into these formulae. This can be evaluated at any frequency f, and the frequency coverage and the number of sampling frequencies can be chosen to fit a particular application. We will be dealing with uniformly or almost uniformly sampled light curves, so the standard choices of the frequencies corresponding to the length of the data and the Nyquist frequency will be used. The number of frequencies is chosen to deliberately oversample the periodogram to constrain the shapes of the peaks accurately. They usually go from thousands to tens of thousands. This is an advantage over the usual common Fourier spectrum, since in the Fourier case the number of frequencies is limited and precisely governed by the data. And with the LSP, the Lomskargul periodogram, we have more freedom. And basically the LSP is based on an assumption that the examined signal can be decomposed into sinusoidal components. Oversimplifying, it's a fancy Fourier. So as an example, let's take the sequence of the sunspot numbers, which has this well-known 11-year cycle. And indeed, in the LSP, you can see some peaks, and the most prominent is almost exactly at 11 years here at the dashed line. So this looks very convincing, and the LSP in general was actually designed with an application in identifying periodicities in stars or asteroids and so on, and works well here also as presented. Now, often one wants to examine the overall shape of the PSD, and the most important example is the power law, 1 over f to the power of beta, which in a logarithmic space is a straight line with slope beta. Frequently encountered is also a power law which flattens out above some critical frequency f0. So there are two components in the PSD, and above f0 the white noise dominates over the power law component. And we can also have a PSD consisting of two power laws with a smooth transition from the low frequency index beta 1 to the high frequency index beta 2 occurring at some break frequency. And the constant C in these two cases is the so-called Poisson noise level coming from the uncertainties in the individual measurements. That is, if one observes a value of 20 plus minus 1, it can actually be slightly above or below 20. Then let's say one observes 21 plus minus 1, which again can in reality be slightly off, though with a different magnitude or direction than the previous measurement. So these uncertainties introduce a bit of randomness to the observations, an additional randomness, and the higher the noise level, so the bigger the errors or the smaller the signal to noise ratio, to put it differently, the more the actual signal will be buried in the observational noise. So the Poisson noise is more often than not a limitation of the equipment or the background radiation of the sky that obscures the signal, more for dimmer sources. So it's usually nothing really physical in the source itself. I mean this constant level C. So this was one thing. Let's go to wavelets, which in essence are wave packets, constrained in time oscillations with a fixed primary frequency. So there's a bunch of different wavelets which can be complex, like this Morlet wavelet, where the real and imaginary parts are blue and red, respectively, or this purely real Haar wavelet. The Morlet wavelet is actually a cosine within a Gaussian envelope. And now, given another wavelet, like this basic wavelet, one can form an orthonormal basis called a dictionary and composed of so-called child wavelets by a translation and rescaling of the mother wavelet. And this is best illustrated by a demonstration that I will somehow need to switch to. So let me stop sharing for a moment, switch to another window and go back to you. Okay, this seems to work quite easy. So do you see this?
Yes, we do.
Notebook. Okay, so everything works. Great. So the wavelet can be squeezed and expanded by changing the scale parameter and moved around left and right, translated as well. And the same applies to the Haar wavelet, which has a different this rectangular shape. And there are also lots of other wavelets like this so-called Mexican head, or a whole family of the so-called Daubetschis wavelets. Yeah, so, and many more. So again, fast switch. Yeah. Okay, so given a signal X, since child wavelets form a basis, one can decompose the signal into wavelet components. This works similarly to the well-known Fourier case. In the Fourier decomposition, one decomposes the signal into a combination of signs, each with different base frequency and with different coefficients indicating how much power is carried by a given frequency component. Here it is similar, just that instead of only the frequency corresponding to S, there is also the location L. And psi here takes the role of the e to the e times frequency part of the Fourier transform, which gives rise to the sign, which is actually infinite in the sense that it doesn't start at a particular point and then end, being eternal, while wavelets are localized in time. So if one put here just a sign and drop the the translation from the W coefficients, one would basically retrieve the Fourier transform. So the wavelet coefficients are obtained as an L-square scalar product of the basis with the signal in the usual way. And then finally, the power in the so-called wavelet scalogram is obtained also as a squared modulus of the coefficients. And let me again switch to another demonstration. Okay, so let's say we have a signal that initially has a frequency of 2 pi, and after 10 units of time it doubles to 4 pi, then to 6 pi, and then to 8 pi at the end. So if one did an LSP, there would be 4 peaks corresponding to the localizations of the components, and the reconstructed signal would be a linear combination of signs, and not a chirping signal like this initial one. So what we do is take a wavelet with a given scale and sweep it, and sweep it along the signal. At each point, we integrate to get the corresponding wavelet coefficients. Then we can take another scale and repeat this again. So, and for smaller scales, and so on and so on. So in the end, we can obtain a plot like this, showing that at times from 0 to 10, there was a signal with a frequency corresponding to some given s. S is actually proportional to the period, so it's the inverse of the frequency, and the proper units can be figured out and normalized. But there is no power at later times at this scale at times greater than 10. But then again, there's this segment when the power corresponding to some other s was high, and similarly for the next portions as well. So one can see the leading period overall decreases in time. So this is basically the methodology used also to examine fast radio bursts or gravitational waves. Okay. And now I can go back to the presentation for the rest of the talk. Okay. So let's take as an example again the sunspot number sequence. There was a strong component identified at an 11-year period, and indeed the scalogram presents a more or less constant and persistent modulation throughout the time series at about 11 years. Moreover, one can see a fall in power around here, which corresponds to the so-called Dalton gap. So a mindful examination of the scalogram allows to deduce both the overall and minuscule behavior of the analyzed data. Moreover, we see here something at the period of 100 years, which after a closer look at the sequence, looks like a sinusoidal envelope, like here in the upper part. So at the beginning of the sequence, there's only part of the cycle starting with low peaks, and this is represented in the scalogram as a band toward lower periods. And this red continuous line is the so-called cone of influence, which is actually the region below these lines. And it depicts the region where the finite length effects are significant. That is the influence of the edges of the time series, so to speak. So this 100-year cycle is there, but one has to be very, very cautious when interpreting it because of the cone of influence. So a longer time series in this case would lower the cone of influence, so one could then get a significant estimate of this 100-year cycle. Yeah. Now, sorry. Okay. Now, what is of importance is to assess which features are actually statistically significant. And when dealing with global periodograms, like the LSP or Fourier, one simulates lots of stochastic models believed to underlie the overall observed PSD, and then checks which spectral features in the observed signal exceed some given significance level, hopefully at least 3 sigma, say. One could in principle do the same for the scalogram, and the method we implemented in the package WavePal, which is suitable also for highly irregular time series, employs a so-called karma stochastic model as the background model for the variation. Karma stands for continuous time autoregressive moving average. So it's basically a continuous time ARGMA. It's not crucial here to go into details, but karma's PSD is quite flexible. It can be either a Lorentzian or so a white noise transiting to a power law. It can contain spectral breaks, peaks, or some other weird features as well. And the magenta contours on this scalogram here denote the 3 sigma significance level against the best fit karma model. And the signal itself here is just a mock one with implicit long and short term periods, roughly revealed here at these bounds, like below 30 days and about 100, something like that. And I will demonstrate later the trending. The signal is important to highlight the interesting features to deal with the non-stationarities. And the last method that I'd want to talk about is the AT plane, spanned by the fraction of turning points, T, and the upper value A. A turning point is a point where there is a swing from increase to a decrease, or vice versa. So these two blue peaks and these two valleys are turning points, and these two reddish segments are not. So having 3 consecutive points, one can arrange them in these 6 ways. For a white noise sequence, all of these are equally probable because each point is independent on any other. So the expected value of T is 2/3. Now, in general, the probability of each pattern can be very non-trivial, like in the ARGMA processes or power laws, Brownian motion, etc. So T can be quite different from 2/3, ranging from 0, when the whole sequence is monotonic, to unity, when the series is strictly alternating, but not need to be periodic or ordered in any way. It can be also like chaotic. So one can say that a series with T greater than 2/3 is more noisy, and with T less than 2/3 is less noisy than white noise by comparison. And the upper value, in turn, is the ratio of the mean square successive difference to the variance. The successive differences actually form a difference series, that is a series of differences, and hence it can be written as a ratio of the variance of such differentiated series to the variance of the original series. So this is some form of a gradient. And A is normalized so that it's equal to 1 for white noise and can range from 0 to 2. And again, A greater than 1 can be called more noisy than white noise, like the similarly as to the T case, and A smaller than 1 is less noisy than white noise. And finally, both A and T attain small values for very smooth curves and high values for very rough or jagged ones. So to illustrate this, let's take simple power laws. The red line here corresponds to pure power laws with increasing values of the index beta leftwards. And when it increases, the path in the AT plane is curved and goes to the regions of higher smoothness. When some white noise is added, the paths and the corresponding points with the same beta are raised and dragged closer to this point corresponding to white noise. This makes sense since when since when white noise is injected in the data, it will alter the probability of obtaining a turning point and will affect the gradient, the ruggedness of the series. But even for a high level of white noise, when t is close to 2/3, the values of A can be very different, hence allowing for example, classification. And indeed, this method has been already successfully used in classifying global markets, diagnosing heart diseases, or even discerning patients with epilepsy. It turns out to be so sensitive that in one study it was able, for the very first time, discern if the patient had open or closed eyes based only on the EEG reading. And moreover, it is prospective in distinguishing chaos from noise and regular behavior as well. Okay, so that would be the introduction. And let us now consider as an example a very recent finding from just a few weeks ago of a group, Smith, Roberts, and Perman, who analyzed the RXTE X-ray light curve of this Seyfert 2 galaxy, NGC 4945. And this in the upper plot, this is the whole available light curve, and it has different segments, but let's focus on this last one with the longest span of over a year and almost 200 points. It is irregularly sampled with no big gaps within. And in the lower part, there is the magnification of this part, and one can see there seems to be some recurring variation in it. So one way is just to feed it to the LSP and see what happens. And if we do it, well, we've got a peak, okay, at the period of about 37 days, but its significance is only 1.7 sigma. So it's way too low to consider it a QPO or a discovery of anything. But let's take a look at the light curve again. At the beginning is this erratic kind of segment, which is a downtrend. So maybe let's just take only the part after point A here, so everything rightwards. And indeed, in this case, we now see a peak with a considerable significance, about 4 sigma. But actually, the authors themselves considered the last segment starting from point B here, lasting about 190 days. And the LSP of this part reveals a peak with about a 4.5 sigma significance. So all good, there is a peak, but this was like one needs to first locate the QPO region to even detect it using the LSP. So that seems to be a very efficient and robust way. But now what obviously comes to mind are wavelets. And indeed, there is this nice, constant, and quite persistent modulation visible here at the 3 sigma significance, and starting also roughly at about point B, like the authors isolated. But this gives an immediate overview of the whole spectral structure of the examined light curve and the significance level too. Actually, I haven't seen a scalogram with contours depicting statistical significance in the astronomical literature, just the analysis of the LSP and then showing that there is a feature in the scalogram computed with another implementation that we are using here. But then again, the significance of the LSP and on the scalogram are different, as the latter on the scalogram is smeared over a 2-dimensional plane, while the global periodogram is a projection of all the power at a given frequency on the vertical axis. So in short, wavelets are a powerful tool in analyzing the PSD and searching for some features. Now, A note about the significance. I think it's well known that 1 sigma corresponds to 68%, and that 2 sigma is roughly about 95%. But in everyday life, when we say that something is 99% certain, such a high percentage virtually symbolizes certainty. Like, if one would know that tomorrow there will be 99% chance to be injured in a train accident, well, he wouldn't go near the railway at all. While on the other hand, if there was a 99% chance of winning millions in a lottery, the ticket sales points would be stormed with buyers. But in fact, 99% is just merely just over 2.5 sigma. And basically we need more, like 3, 4, or 5 sigma to talk about the reality of a phenomenon. And let me illustrate this with a story. In 1976, an LHC team led by Leon Lederman, a later Nobel Prize laureate, announced in Physical Review Letters discovery of a 6 GeV particle with a significance over 98%. The paper actually used a phrase 1 in a 50 chance. So they gave the particle a name epsilon, but only a few months later, when more data was accumulated, it turned out this presumed particle vanished in the noise. So the mere 2.33 sigma significance changed the premature epsilon to the now known upsilon, a pun to Leon Lederman. But later, only the next year, in 1977, the team published a discovery, on this time on a 5 sigma level of a 9.5 GeV particle, and they owned their previous mistake by using the name epsilon. So the epsilon is a real resonant particle, while an upsilon is a discovery that doesn't exist. So since then, in particle physics, the 5 sigma level is an ultimate must. But in astronomy, we generally use the same principle when it comes to discovering sources like gamma ray emitters or radio sources. I mean, to ascertain if the source is even on the sky or not. But curiously enough, when it comes to detecting transient phenomena, the required level is greatly lowered, sometimes with detections being claimed at a less than 3 sigma level. And actually invoking a 5 sigma level would conform to the standards of the discovery, although there would be very, very few QPOs discovered on such a level, maybe just 1 or 2 even. While the 3 sigma level should constitute a candidate. So either way, there is also this other issue. What actually is a QPO? I mean, it's an oscillation. It's periodic, but not precisely, because it's quasi, meaning similar to, but not exactly. So let's say there's just one cycle, one bump in the light curve. So basically, this isn't a QPO. It could be anything, a flare, a glitch, like anything really. But then if there's only one, where's the periodicity in it, since it doesn't repeat even once? So that seems clear, that more than one cycle is required. What if there were 2? This seems recurring, but at what odds? Then they say 3 is a charm, but since we always want more and more data, maybe we should require 4 or 5 cycles or more. But then again, on the other hand, we are facing a barrier, because QPOs are usually transient in the sense that they start, last for some time, and then fade away. So some phenomena, like gamma ray bursts, may inherently prevent us from obtaining a high significance. On the other hand, also, how constant do we require the cycle to be? Let's take, for example, the gravitational waves from a merger. This is an oscillation with a decreasing period, and then it abruptly ends at the merger. It's usually called a chirp or a chirping signal. So we can think this way. You observe a neutron star orbiting a black hole, and you look exactly in the plane of the orbit. Every revolution, you see basically exactly the same image, a neutron star in front of the black hole. Half an orbit later, the neutron star will hide behind the black hole, and then you will see the same image again. So basically, every one revolution, the configuration is exactly repeated. So this is definitely some kind of a recurring phenomena and maybe some kind of a QPO. I don't have a particular answer or a recommendation here. This is something that basically should be debated in the community. I mean, the proper definition of a QPO, like what we are actually really looking for. Great. So let us now proceed finally to some actual results. Recently, in a paper of ours, we analyzed in great detail the Fermi-Lat gamma-ray light curves spanning 10 years of 11 of the brightest or otherwise famous blazars like Macaran 501 or 3C454.3, using a variety of methods, and performed also exhaustive benchmark testing of their reliability. I obviously don't have time here to describe everything in detail, so this will be just about a few of the selected results. Anyway, there were 5 BL-LAC type objects in our sample, including the famous neutrino emitter TXS0506, and 6 FSRQs, including PKS 1830, which is a gravitational lens in the gamma rays. In 8 of these 11 sources, some QPOs were already reported in the literature, though with quite various significance from below 3 sigma, sometimes reaching something like 4 or 5 sigma. And the power law shapes have beta indices falling mostly in the range between 1 and 2. So
sorry for interrupting, but these are the QPOs reported strictly for the Fermi-Lat light curves, or in general?
No. These are strictly Fermi-Lat. No optical, no X-rays, no nothing else.
Okay, thanks.
Yeah, and regarding the beta indices, this neutrino emitter, the Texas source, hadn't been examined in this regard. So basically, this is how the PSD looks like for that source, with beta roughly being of the red noise type. And to clarify, we analyzed 3 versions of the light curves for each object with a 7, 10, and 14-day binning. That is the time step between the observations in the binned light curves, just to ensure the consistency of the obtained results. And regarding the QPOs per se, we confirmed the quite famous 600-day QPO in PKS 2155 with a persistent 3 sigma modulation throughout the whole light curve. Compared with several previous works, there has been a gradual decrease in the leading period. And this is the only QPO out of the 8 reported for the objects in our sample that we detected in the wavelet scalograms on this compelling 3 sigma significance. In case of the gravitational lens, this PKS 1830, one can at first think there's a new QPO because there's this peak here. But a closer look at the scalogram shows that these lone isolated 3 sigma contours cannot be confidently described as a QPO. They all correspond to different leading periods, are separated in time, and the features corresponding in the light curves do not show enough persistence. So based on the global periodogram, this one on the right, one would conclude there's a peak above 3 sigma, but the scalogram doesn't support it being a real QPO. And recently, the importance of utilizing various methods for assessing the PSDs compared with the stachylogram analysis and a visual inspection of the light curves in question was also pointed out. And fortunately, a rigorous use of wavelets is being advocated. We also observed hints of a quasi-periodic modulation in another object, PKS 0716, with a much higher period exceeding 1,000 days. So given the length of the data, this definitely should be treated with caution till it's observed for a longer time, but some other authors also pointed this one out as an interesting candidate. And there was also this curious feature that looks like a chirp as the period greatly and systematically increases over time. Other authors reported as well some leading periods, but those were based on an LSP approach. And here we see this apparently a single feature that is evolving in time. What is actually novel and non-trivial is that the blazar types separate in the AT plane. So to give an overview, this dark gray region in the background is the region of availability for the power law plus Poisson noise processes, with lighter gray bands around it denoting the errors corresponding to the length of the examined light curves. And the cold colors of the dots denote FSRQs, while the warm colors show BL lux. And this vertical line is a demarcation between the two, and there is this one lone outlier here. Now, this separation is not that trivial. One might say that the FSRQs have, on average, higher beta indices and are brighter than BL lux, so less noisy in the observed light curves. So should be placed on the left part of the plot. But this is not the case, since this purple line on the right shows the beta equal to 1 case, and its path when the Poisson noise level, so the white noise contamination, is increased. Such lines for other beta would be similar in nature, so this is not that trivial. Hence, the separation of blazars in the AT plane seems to be a genuine feature. And is supported also by our previous findings that blazar candidates behind Magellanic clouds, in the optical, in this case, also occupy different parts of the AT plane depending on their supposed classification. Okay, so on to the most recent preliminary result concerning gamma ray bursts, utilizing the already mentioned methods. In general, we consider the Swift catalog of over 1,300 GRBs. We consider only prompt light curves in a 64 millisecond binning to get a uniform resolution for all of the sources. We consider only confidently long GRBs, that is those with durations more than 3.2 seconds, to get more than 50 points in order to get a good sampling. And to keep the sample homogeneous, we exclude confirmed short GRBs with extended emission. And in the end, we end with 1,160 GRBs. Those PSDs, whose PSDs were fitted with the previously mentioned models, the power law plus Poisson noise, and the broken power law. We attempted an AT plane classification and searched for QPOs. So just I will just go over the PSDs really fast. These are some random examples of the pure power law of the best model in the upper left corner, fitted to the binned PSD. Then there's this power law with Poisson noise, and two instances of a smoothly broken power law. Some PSDs were quite peculiar, like this one on the bottom right, that basically consists of a peak. Like this whole PSD is just one peak. And in this case, the small frequency index beta 1 is negative. So some descriptive statistics, the power law betas are extend to about 2. When Poisson noise is introduced, this is between 1 and 3 mostly, with a tail. And the smoothly broken power laws can be as steep as 6, with some more with some heavier tail. And the time scales at which the break between the beta 1 and beta 2 occurs is roughly between 1 second and 100 seconds, with a logarithmic mean at about 30 seconds. And having these PSDs types in mind, the locations in the AT plane are surprisingly unremarkable. We anticipated getting clear clusters, but that's not the case. Although one can see some overdensity here around 0.1 2/3, but that's the location of white noise, and many GRBs in the catalog are very noisy, dim, and with low signal-to-noise ratio. And using only the high-quality data doesn't reveal any substructure either. And within each PSD type, the power law case behaves as expected, with higher beta further to the left of the plot, indicated by the size of the points here. And but the power law plus Poisson noise and broken power law behave erratic, likely due to the high noise contamination. Maybe I will skip this to save time. And the first QPOs in gamma ray bursts were reported back in the 70s, and it consisted after the initial outburst of a steady modulation with about an 8-second period, lasting for about 20 cycles. And this is probably the highest significance QPO ever detected in a GRB. More recently, there was some interest about 10 years ago regarding some Swift GRB, which also seemed to exhibit a 8-second modulation on top of a pulse. The fast rise exponential decay shape. There were a few works at that time utilizing data from different spacecrafts like Integral Suzaku and so on, but they were yielding very varied results regarding the significance, even for data from the same instrument, but analyzed with a bit differently by different groups. So this is the first GRB whose scalogram I will show. I mean, this is this event from the 10 years ago. And we see here quite a constant and persistent modulation at the reported about 8-second period. So it's 8 seconds lasting for 80 seconds, so it's more or less 10 cycles. Now, just for illustration, I will be showing a few sinusoidal fits to the time series that were done using the periods identified from the scalogram. But I like to stress that this is purely for demonstration here, just to guide the eye, to visualize the character of the modulation. This is not that we are fitting a sign and claiming a QPO. So the, yeah. And this cycle here is slightly different than the one on top here, because first I fitted and removed this pulse, and the wavelet scalogram, the implementation that we utilize, takes care of the trending by carefully fitting a polynomial. Okay, so a few plots, and that will be almost it. Here is a series of apparent harmonics, maybe, with an overall increasing period, which manifests in the light curves as systematically growing separation between, there is a peak also, 2 peaks here in the middle, between the successive peaks. And the sinusoidal fits are not good here, since each of these pulses is non-sinusoidal, and so describing the whole light curve as a combination of signs is not appropriate. So in this case, there is this 40-second modulation, but actually the first sign that is identified is about 100 period, and it's just exceeding the range of the period shown in the scalogram here. But on top of it, there is again a 40-second period, roughly consistent with this identified QPO here. Here is a similar feature with a 17-second QPO, neatly in this case visible as an approximation of a sine. And another example with basically 2 main modes, again on top of a pulse that was, for the sake of this illustration, removed. And this is the probably most pleasant case of a very clear 8-second QPO lasting for about 4 cycles. And this also quite nicely fits the sinusoidal scheme, and this is like the only prominent feature in the whole scalogram. But this best illustrates that additional sine waves might actually ruin the fit, because it may lie well on some portions of the fit and fail for some others, because the modulations that are present here last only in parts of the light curve, and the sines are fitted globally to the whole light curve, even to the parts where the modulation doesn't exist. And there's also a bunch of complicated, much more complicated than the ones that I just showed, features, difficult to interpret, all looking kind of like an extraterrestrial ghost lurking at us from the deep space. So the unanswered question is what causes these presumed QPOs in GRBs? In general, the prompt emission is of synchrotron nature and comes from colliding shells within a relativistic jet powered by accretion of a remnant material. There is one worked out physical scenario pertaining to short GRBs, but we analyzed only confidently long ones, so it's unclear whether the same mechanism applies or not. And some other from the top of the head interpretations might be that these QPOs are due to some mechanical modulations in the disk or jet, while the origin of chirps, if real, is even more mysterious, but might be caused by emission during fallback of remnant matter from a fragmented disk, inspiring on trajectories inside the innermost stable circular orbit. So this has a decreasing period that might be manifested as a chirping signal in the light curve. This needs to be calculated more precisely. That is the time scales, the required masses, and so on. So basically the governing mechanism is unclear. So there is definitely place for future explorations. So to sum up, the global periodograms like the LSP are not a very good way to search for QPOs. Wavelets should be resorted to, and while blazar subclasses are separated in the AT plane, it was actually not observed for GRBs. for which in turn several interesting features in the scalograms were observed, with many QPO candidates and some ghastly appearances as well. So there were also lots of analyses and discussions I couldn't present in this short presentation, like the ARMA and KARMA modeling or the Hurst exponents and so on. But those have already been gathered or will be presented in full papers. And that's a good place to stop. Thank you for your attention. Sorry for taking it a bit too long.
Thank you very much. Clapping hands. Yes, I put the sign of the clapping hand. Thank you very much for this very comprehensive presentation.